This is Theories of Acids and Bases, Part 2. In Part 2, we'll be talking about buffer solutions and metal aqua ions and complex ions. The assessment criteria we'll be addressing are the following: understanding the actions of acidic and basic buffer solutions qualitatively in terms of equilibria, be able to calculate the pH of a buffer solution, looking at the various acid-base theories and looking at their conditions, their strengths, and their limitations, recognizing and knowing the structure of metal aqua ions, understanding the behavior of these metal aqua ions and their reactions with ammonia, hydroxide, and carbonate solutions. We'll look at ligand substitution with similar and dissimilar sized ligands. We'll also look at ligand solutions in terms of complex ion stability. And we'll recognize the existence of bi- and multidendate, sometimes called polydendate ligands, and understand the chelate effect or chelation in terms of entropy and free energy. Let's look at the first assessment criteria. Understand the actions of acidic and basic buffer solutions qualitatively in terms of equilibria. Well, first off, a buffer solution is a solution that is resistant to changes in pH if you add small amounts of acid or if you add small amounts of base. If you have an unbuffered solution and you add acids and bases, you can get very significant changes very quickly. Water has a pH of 7. If you add 1/100th of a milliliter of 1 molar HCl, that water's pH goes from 7 to 4 without a buffer. Looking at adding a base such as sodium hydroxide, 0.01 milliliters of 1 molar sodium hydroxide, the pH goes from 7 to 10. So without using buffers, you tend to have wide ranges of pHs when you're trying to measure small changes. Buffers are usually soluble salts, fully dissociated in solution, no matter whether the acid is a strong acid or a weak acid. And so this excess of the salt's ions in solution acts as a backup or an extra place or a reservoir to resist pH change. You should be able to calculate the pH of a buffer solution. The pH of a buffer solution depends on the equilibria that exists. We're going to look at an acidic buffer for a generic weak acid and its salt. The weak acid, HA, the salt, Ma. You can look at examples for generic strong acids and its salt, strong bases, so on and so forth. But we'll just do one. Well, what about a generic weak acid? We know that a weak acid dissociates, but the initial concentration of the acid is about what it is at equilibrium. However, the buffer, the salt, is fully dissociated. So that would be equal to the concentration of A minus. So if we're going to look at the pH, we'll first look at Ka. Ka is the hydrogen ion concentration times the A minus concentration divided by the concentration of AH. Rearranging, we see that H plus equals Ka times HA. If you take the negative log of both sides, we get the pH. So the pH is equal to pKa plus log to the base 10 of the salt divided by the acid. Now let's look at a video that talks about some use of buffers in both biology, biochemistry, and also generic chemistry.
Welcome to buffers. The term buffer generally refers to something that lessens or absorbs the impact of something else. In chemistry, though, and in biology, buffers have a more specific meaning. They refer to a substance that prevents or resists a change in pH. Why is that necessary, though? Why would we want a substance that prevents or resists a change in pH? Well, let's look at the example of human blood. In humans, the pH of our blood has to stay at around 7.4. It's typically maintained at this level, and that's for optimal functioning. And the pH can change a little bit, but it really needs to stay in a narrow range around 7.4. In fact, if we go above 7.8 for blood pH, or below 6.8 for even a few minutes, it can result in death. Well, you may be wondering, Mr. Isaacs, what's the big deal? I totally stopped injecting myself with hydrochloric acid like last week, so why would my blood pH change? And that's a good question. Why would your blood pH change if you're not introducing acids or bases into your blood? Well, what you may not realize is that every single one of your cells uses oxygen and then gives off carbon dioxide. And this carbon dioxide enters the blood. And your blood contains water. And the water that's present in your blood can react with the carbon dioxide in very small amounts to produce H2CO3 carbonic acid. And as its name implies, carbonic acid is an acid. So this reaction has been happening your entire life because your cells have always been producing carbon dioxide as they use oxygen. And if small amounts of acid are constantly being produced in your blood, how is it that your pH is able to stay at 7.4? And the answer to that, the answer to how your blood is able to stay within a certain range of 7.4, is that your blood contains something called a buffer. And a buffer is essentially a solution, so something dissolved in water, and it could be a solution composed of one of two things. Either the solution is made up of a weak acid, and also along with that weak acid, its conjugate base, or the solution could also be made up of a weak base and the conjugate acid of that weak base. So let's see what this looks like. We'll use a weak acid. So we'll start with acetic acid, a weak acid. And the formula for acetic acid is HCH2COO. That's one way you can see acetic acid written. And acetic acid can ionize into H plus and the acetate ion. So the acetic acid is our weak acid. And we know that means, because it's an acid, that it's a proton donor. And we see the proton being donated right here. So the conjugate base is what's left over after the proton's been donated. And that's this acetate ion here. So this is the conjugate base. So then how do we make a buffer knowing what the acid and base are? Well, we're going to take equal amounts of the weak acid, so some equal concentration of this, and we're going to combine it with the same concentration of some salt that contains a conjugate base. So I could use sodium acetate, because this salt will dissociate in water and give me this acetate ion, the conjugate base. So I make the buffer by using equal amounts of the weak acid and a salt containing the conjugate base. So now the big question is, how does this buffer work? Well, if I take some container, fill it with water, and I add acetic acid and my acetate ion containing salt, I now have a buffered solution in this container. Now this buffer is going to resist a change in pH. That means it's going to resist an increase in pH and resist a decrease in pH. So let's look at those two cases separately. So let's start by looking at what happens when I add a strong acid. I'm going to choose hydrochloric acid as my strong acid. And I know that hydrochloric acid fully dissociates into H plus and Cl minus. It completely dissociates because it's a strong acid, and that's the definition. So by adding hydrochloric acid, what I'm really saying is that I'm adding hydrogen ions, or protons. Most of these H pluses, most of the H plus ions, will react with the acetate ion that's present and form the acetic acid. So if most of the H plus is used in this reaction to create more acetic acid molecules, which by the way acetic acid is one of the components to the buffer, if most of the H plus is used up in this reaction, then there won't be H plus freely floating around, meaning adding a strong acid did not result in an increase of hydrogen ions. So I won't really see the pH change by that much. There'll still be a small change, but not nearly as much as we would see if these H plus ions from the strong acid were all just floating around. We can also look at what happens when we add a strong base. So for our strong base, let's consider sodium hydroxide, a very common strong base that we've been using. Sodium hydroxide we know dissociates completely into Na plus and OH minus ions. And we know that these OH minus ions, these hydroxide ions, would increase the pH of the solution. The greater concentration of OH minus ions would drive the pH up. However, just like we saw with the acid, most of the OH minus ions produced here would instead undergo a neutralization reaction with the acetic acid present in the buffer to produce water and the acetate ion, which is the conjugate base again. And because most of this OH is used up in this neutralization reaction, we don't see the pH increase as much as it would otherwise. So this is just one example of a buffer system. We have acetic acid and its conjugate base, the acetate ion. In your blood, the buffer that's used there is carbonic acid, H2CO3, and its conjugate base, HCO3, the bicarbonate ion. So this generally describes how to create a buffer and how a buffer works to prevent changes in pH. There are also two more things that are helpful to know when you're dealing with buffers. And the first is that to create a buffer, it's important to know how to quickly recognize a weak acid and its conjugate base. So if you have some weak acid of the general formula HA, you should be able to remember that it dissociates into the free H plus ion, the free proton, and this A minus ion. So finding the weak acid and conjugate base pair is always going to be this HA, something with a hydrogen, and then something that has lost the hydrogen, the conjugate base. So anytime you're given a weak acid, you can very quickly find its conjugate base by remembering it's just whatever the A is in the acid with a negative charge because it's lost a proton. So we saw that with acetic acid, that just became the acetate ion. And we also saw it with the blood buffer, which is carbonic acid that has lost one proton, and we get its conjugate base. So this general formula HA and A minus is a very useful thing to remember. The second thing that's important about buffers is that they have a limit, they have a capacity. It's called buffer capacity. And the buffer capacity basically refers to how much acid or base the buffer can absorb and still resist the change in pH. Because eventually, if one of these things is used up, if the weak acid is all used up neutralizing a base, or the conjugate base is all used up neutralizing a strong acid, then it won't be able to prevent that change in pH anymore. So the buffer capacity is how much the buffer can absorb and still resist the change in pH. And we can look at two examples of this. If I make a buffer with 0.1 molar acetic acid and 0.1 molar acetate ion, this is going to have a much greater buffer capacity than if I did 0.001 molar acetic acid and 0.001 molar acetate ion. And the reason that this higher concentration buffer has a greater buffer capacity is because there are simply more particles available to absorb acid or base. There's another neat thing about buffer capacity, and so we're going to explore this solution a little bit more. when we make the buffer of acetic acid and its conjugate base, it basically fixes the pH at about 4.8. So now if we look at this buffer capacity thing again, the first solution that has a 0.1 molar concentration of each component, the higher concentrated buffer, has this pH 4.8 it's sort of fixing the solution at. Just because it's more concentrated, that doesn't have any effect on the pH that the buffer works at. This very low concentrated buffer also fixes the pH at 4.8. So buffers work independently of the concentration. The only thing the concentration of the buffer affects is how much acid or how much base it can absorb. That wraps up our lesson on buffers. Write down any questions you have in your notes and bring them with you to class.
The next assessment criteria asks you to recognize various acid-base theories. There are three: the Arrhenius's, Bronsted-Lowry's, and Lewis, and understand the conditions in which each may be used. Arrhenius historically was the first to come up with a workable definition of acids and bases. An acid is a substance that provides H plus ions. A base is a substance that provides OH minus ions. Arrhenius's theory and definitions work in aqueous solutions, and only where we have acids and bases that have H plus and OH minus. Bronsted-Lowry expanded that idea to say that an acid is a proton donor and a base is a proton acceptor. Now that can be used in solutions. It can be used in the mixture of gases that are acids and bases. It can be used in a variety of situations. Lewis is the most recent definition of an acid or a base, and that says that an acid is an electron pair acceptor and a base is an electron pair donor. So that means any electron pair capable of accepting or donating an electron pair is an acid or a base. Probably the most comprehensive theory of what an acid or a base might be. The next assessment criteria is to recognize and know the structure of metal aqua ions. A metal aqua ion has a metal ion at its center. If you look at the picture, you see in this case it's iron with a number of water molecules surrounding it. They can be considered to be attached to the central ion by a kind of covalent bond called a coordinate bond. The ions or molecules that surround the central metal ion, in this case H2O, is called a ligand. Each of the 6 water molecules are attached to the central iron Fe3 ion via coordinate bond using one of the lone pairs of the oxygen. Notice they're attached to the lone pairs. Now let's take a look and see how these ions behave when they mix with other things. So for example, let's take a look at a metal aqua ion. The previous slide talked about iron being the central and water being around it as ligands. Here we have an M, a general case, being the metal, and it's surrounded by water. It's a +2 ion. It's easier to look at this picture as an ion, a metal aqua ion, as the metal plus a hydroxide in an ion form plus an H plus, a proton donor, available. Now, what happens if you add hydroxide ions to this equilibrium equation? There's two possible reactions. I think you're fairly aware of what happens from Le Chatelier's principle. If you add hydroxide ions, what you'll do is move the position of the equilibrium to the right, and the hydroxide ions combine with the H plus ions, removing them from the equilibrium. Now, that is what could happen. But statistically, there is a far greater chance of a hydroxide ion hitting a metal ion than of hitting a hydrogen ion, because there are many more of these hexa-aqua ions present. If you do that, you get exactly the same complex ion formed, and it looks like a ligand exchange, but it isn't. The hydroxide ion has removed a hydrogen from one of the ligand water molecules, and it's made the reaction virtually one way. You lose the equilibrium nature. So we've just looked at what happens when you add hydroxide to a complex ion. There's two directions that it may go. The one on the right is statistically the greater one that would be happening. What happens if you add ammonia? There's two alternatives as well. Again, if you add ammonia, the chances are that the position of the equilibrium moves to the right, and it will create, with that H plus ion, ammonium ions. But, just as we've seen before, statistically, there's a far greater chance of the ammonia molecule hitting a hexa-aqua metal ion than finding that hydrogen ion. If this happens, you get the same new complex ion formed as above. And so notice that this is still reversible. Ammonia is only a weak base, not like we had when we added OH, which might come from a base like sodium hydroxide. So we still have a equilibrium situation here. Well, what about a carbonate? Well, two choices again, but in this case, carbonates are carbon and oxygen. So you get a little bit different progression than we saw with hydroxide or ammonia. You get a two-stage reaction. You get carbon dioxide. So if you have that H plus, and the carbonate gives hydrogen carbonate and water, more H plus goes to carbon dioxide and water. But statistically, again, there is a far greater chance of a carbonate ion hitting a hexa-aqua metal ion than it is hitting a hydrogen ion. And so you see the carbonate ions keep on removing hydrogen ions from the complex until you end up with a neutral complex. And you see that because it turns into a precipitate. If you notice, CO2 is given off at each step, and a precipitate of the hydroxide is formed. So there is different outcomes whether you are adding hydroxide ions, ammonia ions, or ammonia and carbonate ions to a hexaquametal ion. Well, let's take a look about these ligands. Remember, the ligands were the things attached to the metal ion in the center. A ligand substitution occurs when a ligand in a complex ion is replaced by another ligand. If the ligands are of similar size, the coordination number of the complex ion doesn't change, and neither does the shape. For example, water and ammonia are ligands that are similar in size and are both uncharged. That means that they can be exchanged fairly simply. You do get a color change, but they can be exchanged fairly simply without a change in coordination or real shape. But if ligands are different sizes, there is a chance of coordination number and change of shape. Chloride, a chloride ion, or a chloride ligand are much larger than water ligands, and again, because of its electronegativity, have much stronger repulsions, so fewer ligands can fit around that central metal ion. Now, perhaps the best way to explain ligand substitutions is in terms of the complex ion that is formed and how stable it is. Let's take a look at the equilibrium equation that is in the top right between the complex aqua ion, metal ion of copper plus ammonia. It will come up and have a stability constant. The stability constant is nothing more than the equilibrium constant. Now, we've found the equilibrium constant for this first equilibrium equation, and it's in the first top left of the table. You'll notice there that its log, or its stability constant, is 4.25. Now, if you would now look at the left, you can have replacements that happen one at a time. You see those four equations grouped together. Those four equations are reproduced with their stability constant in the table in the bottom right. What you see is nothing more than 1, then 2, then 3, then 4 water molecules being replaced by ammonia. And you see the stability constant decrease as those water molecules are replaced by ammonia. So it is most likely in a ligand substitution that you will see more of the single substituted complex ion than you will see of the double, triple, and quadruple replaced ion. Now, the last criteria that you are asked to look at is to recognize the existence of bi- and multi- or polydendate ligands and understand the chelation effect or the chelate effect in terms of entropy and free energy change. Bi and multidentate are indicators of denticity. All that means is the number of donor groups in a single ligand that binds to a central atom in a coordination complex. In many cases, only one atom in the ligand binds to the metal, so denticity equals 1, and the ligand is said to be monodentate. More than one bonded atom, say 2, is bidentate, 3 is multidentate or polydentate. Multidentate ligands are chelating agents. What chelating agents are substances whose molecules can form several bonds to a single metal ion. In other words, a chelating agent is a multidentate ligand. To the left is a bidentate ligand. Around the metal ion, there are 4 hydroxides and 2 CH2, NH2 ligands. There is an increase in entropy because there are multiple ligands. The greater the number of different ligands, the greater the entropy, the greater the free energy. Let's look at a video that reviews our understanding of complex ions.
If it has a coordination number of 2, then it will be a complex linear shape. If it has a coordination number of 4, then it's either going to be a tetrahedral or a square planar. If it has a coordination number of 6, it's going to be an octahedral shape. So remember, 2 linear, 4 tetrahedral, square planar, 6 is octahedral. Now, the ligands surrounding the metal atom can be substituted in ligand exchange, or otherwise called ligand substitution reactions. If this only happens if the stability of the new complex formed with the new ligands is greater than the current one. So it's all about stability. The complex wants to be as stable as it can. If the new one is better for it, then it's going to be into that form. If it's not, then it stays how it is.
Questions here to start your thinking. One is on the effects of pH, and the other is on metal aqua ions and the effect of d orbitals on the creation of these meta aqua ions. I'd ask you to complete these questions when asked by the instructor, and as well turn them in when I ask as well.